Have you ever noticed that some metals react fiercely with water while others just sit there, unchanged? That's because different metals have different reactivities. These chemical behaviors help us understand everything from corrosion to metal extraction. Metals react with air, water, acids, and even with solutions of other metal salts, and how quickly or intensely they do it gives us insight into their chemical personality. In this concept, we'll look at those reactions, and by the end, you'll be able to rank metals based on how they behave. Let's begin with oxygen. Almost all metals form metal oxides when exposed to air, but the speed and style vary. Take copper, for instance. It reacts slowly to form a black coating of copper to oxide. The reaction goes to Cu plus O2 gives to CuO. Sodium and potassium, on the other hand, are extremely reactive. They burn with a flame and have to be kept under kerosene. Aluminium forms an oxide too, but it protects the metal from further corrosion. Some oxides like aluminium oxide and zinc oxide are amphoteric, meaning they react with both acids and bases. For example, Alto 3 plus 6HCl gives to Alkyl 3 plus 3H2O. And Alto 3 plus to NaOH gives to NaAlO-2 plus H2O. Water reactions reveal even more about reactivity. Sodium and potassium react with cold water so violently that hydrogen gas released actually catches fire. Here's the equation. To Na plus to H2O gives to NaOH plus H2 gas. Calcium also reacts with cold water, but more calmly. Magnesium reacts with hot water instead. Now what about zinc and iron? These metals don't react with cold or hot water, but they do react with steam. Example, 3Fe plus 4H2O gives Fe3O4 plus 4H2 gas. Some metals like copper, silver, and gold are so unreactive that they don't respond to water at all. Next up, acids. Metals typically react with dilute acids to form a salt and hydrogen gas. This is especially true with hydrochloric acid or sulfuric acid. Zinc is a good example. Zn plus to HCl gives ZnCl2 plus H2 gas. You'll see bubbles forming as hydrogen gas is released. But some metals like copper don't react with dilute hydrochloric acid. And nitric acid? That's a twist, it's a strong oxidizing agent. Instead of letting hydrogen escape, it oxidizes the hydrogen to water and reduces itself to nitrogen oxides. So, the metal's nature and the acid's strength both matter. Now here's a classic high school experiment, displacement. A more reactive metal can push out a less reactive metal from its salt solution. Like this, drop an iron nail into copper sulfate and you will get reddish-brown copper deposits. Why? Because iron is more reactive. The reaction is Fe plus CuSO4 gives FeSO-4 plus Cu. Try it the other way, copper into iron sulfate, and nothing happens. This single observation helps us build the reactivity series, a ladder of how eager each metal is to react. So where does all this lead us? To the reactivity series, a list that ranks metals from the hyperactive potassium and sodium all the way down to unreactive gold. The higher up a metal is, the more it reacts with water, with acids, and with other compounds. This ranking helps chemists decide how to store metals, how to refine them, and how to protect them from corrosion. And now you know, just by observing a few bubbles or flames, you can start predicting how any metal might behave.